standards thought that the same thing should happen with light. And the nature of light is of great importance for what we are going to say. So people knew early on, and you will see later on why, that light was a wave. And this is because when two waves superpose, they form particular patterns. They are called interference patterns. And light does that, as two waves of water do, one waves do. So people knew that light was a wave. So the natural question is, if I have waves in water, you require water to have waves. In order to have waves, to have a disturbance, you have to have a medium in which the wave propagates, the wave is formed. So what is the medium that is waving in light? Well, people didn't know it, but they said, well, there must be a medium, and they call it ether. In particular, they call it luminiferous ether, which means carrying light. So in the same way, waves in water require water, waves in the ether require the ether. And people knew a lot about ether. They knew so much, there were many papers written about it. For example, let me show you one. This is a paper published in the Transactions of the Cambridge Philosophical Society. This is the same publication in which Isaac Newton published, right? And this is from 1839. And here you have the title. The title was On the Nature, etc., of the Luminiferous Ether. Many papers about the properties. Since you see all the stars, the light coming from very far away, it couldn't move, it couldn't be dragged, it couldn't be, many things, many properties of the luminiferous ether. What people didn't know is how we were moving with respect to the luminiferous ether, or what was the rest frame of ether. And so the rest frame of ether, so we were the Earth was certainly not moving with respect to the ether, because it couldn't be dragged, Earth is a little planet, so it couldn't be just moving the ether around. We should be moving with respect to the ether. It was something else that people took as a very good indication that there was an ether. It was this. This is a not very good photo of James Clerk Maxwell, Scottish physicist, who in 1965 came up with the equations of electromagnetism. These equations describe all electric and magnetic phenomena, and in particular they describe light. Light as a disturbance of the medium that carries electric and magnetic signals. And there was only one value of the speed of light in those equations. This is what we call c, which is pretty fast, 300,000 kilometers per second. Since there was only one value, people said, that's clear, right? So these equations are valid only if we are at rest with respect to the ether. Only an observer, like in the case of the pond, an observer that is at rest with respect to the pond would see these waves moving with velocity in any direction. In the same way, an observer that is at rest with respect to the ether would see the velocity of light being the same in every direction. Clear, right? Well, but that would imply something very profound, because then I can define the ether at rest as absolute rest. There is a way of distinguishing a particular absolute rest. And everything that is moving with respect to the ether would be in absolute motion. So there was a way of distinguishing absolute rest and absolute motion. Not with respect to Earth. Remember that in the Aristotelian view, Earth was at rest in the universe and everything else was moving. So Earth is not at rest, but there was another way of defining the rest frame. Some people objected this cannot. In any case, there was a way of measuring if that was true, because Earth is moving. Earth is moving. Earth was supposed to be moving with respect to the ether. So if we can see this effect, that actually as Earth moves in the ether, we could observe that light travels at a bit different speed in the direction the Earth is moving with respect to the ether, or in the direction opposed to that. So in different directions, the velocity of light would be different. Are you with me? This is the same as in the font. Any questions so far?
What's the definition of ether?
The ether was this medium that does not exist. Who asked this question? Ether doesn't exist. It was invented until 1905 to explain the characteristics of light by making a story, right? The ether does not exist. Yes, if ether would have existed and Maxwell's equations were valid only for an observer that is at rest with respect to the ether, that means that in any other frame I can measure, through measuring the velocity of light, I can measure if I'm moving around with respect to the ether. And therefore there was a way of defining an absolute rest frame, which was this very important rest frame, which was the rest frame of the ether, singling out one reference frame. In reality, there is no way of saying that anything is at rest. Anything is at rest with respect to an observer, because the observer is moving with the object. But otherwise, you cannot say this is at rest. Right? There is no way of singling out one particular reference frame, one particular type of observer. All right, so we have to wait until the end, practically, of the 1887, the end of the 19th century, for Michelson and Morley to make to perform probably the most famous negative experiment. That means the good thing, the very important thing, is that they did not find what they set out to find, which was the relative velocity of Earth with respect to the ether. So they had, their experiment consisted in a race, like a car race. In this case, it was a race between two rays of light. And they were trying to see if they could find the direction in which the Earth was moving with respect to the ether. If we were moving with respect to the ether, the velocity of light should be a bit smaller. The velocity of light should be a little larger. Right? It was a race between two rays of light and comparing the speed of light in the two directions. They found no difference. No difference. And so what they found was the velocity of light was the same, was exactly the same. Light was found to travel always at the same speed. So think for a moment. Here I have my elaborate experiment. Okay. So assume I'm always throwing this ball with the same speed, okay, with respect to me. Right? Throw the ball. Now I'm running very fast and I throw the ball, same speed with respect to me. It will be faster with respect to you. Right? My sum up to the speed with which I throw the ball, right? Are you with me or not?
Yep.
Okay. Now I shine light. Okay, light. Very bright light. Shine light. Okay. The light is moving with respect to me at the velocity which is 300,000 kilometers per second. Assume that I would be moving very close, with a velocity very close to 300,000 kilometers per second. Right? I am not, but assume I could. Very fast. Right? So, the light is moving with c with respect to me, and I am moving approximately with c with respect to you. This light will still be moving with respect to you with c, not with 2c. Right? It's very strange. Why? Okay? So the velocity of light is always c in vacuum, independently of the speed of the source or the speed of the observer. This is extremely anti-intuitive. Right? And it was then as it is now. Very anti-intuitive. I will mention this attracted, of course, the best minds of the time. One of the best minds of the time was Hendrik Lorentz, the most famous theoretical physicist. And he explained, he wrote all the equations to explain the results of the Michelson-Morley experiment. Why shouldn't, which way should go, but he had no idea why. In fact, he came up with a very bogus idea. Electrons, which form the outer layers of atoms, probably you have heard of electrons, had been discovered shortly before all this happened. And so he said, oh, maybe electrons have something to do with it. Hendrik was. But still, he still believed in ether, but he made all the math of this. So the math of relativity is not new. But you know, I made this long story, and where is Einstein? Einstein was a nobody. He was a German physicist, very young, 25, 26 years old. He was working in a patent office. This is about the least glamorous work that you can think of. A patent office in Zurich. And one of the three absolutely seminal papers that he produced in 1 year, 1905, was this, the special theory of relativity. So he says, first of all, there are only two postulates. The first is, there's no absolute rest. Ether cannot exist. There is no way of measuring, doing any experiment with light or with anything else, that we are in a special reference frame. All observers in all reference frames moving at any speeds would have the same results. So this was just a postulate of relativity, which gives the name to the theory. The second, he said, I postulate the speed of light is constant for all observers in vacuum, of course, because when the light travels through a medium, it changes. But in vacuum, it's always the velocity of light c, independently of the velocity of the source of the observer, as I just said. Of course, there are very important consequences of that. One of the consequences is people agree on the velocity of light. They don't agree on simultaneity. These are two pictures that come from the book that I think you used here. So assume these are two observers. One is inside a rocket, the other is a spaceship, and the other is outside it. Both of them see light coming out at a particular instant from a particular source, right? Now, this person, who is at rest with the source, sees the light reaching both ends of the ship at the same time, right? Because he's equidistant. He's at the same distance, same speed. Are you with me? Same time. Now, the same thing is observed from outside. But of course, for this observer, this ship is moving. The ship is moving. So this end of the ship gets first to the light. And this one is coming apart. So she sees that light reaches first this point, and then after that point. Are you with me? This is very strange. The two observers moving at different velocities do not agree on when two things happen at the same time or not, simultaneously. And this is very important. As Einstein said, all our measurement of time is based on simultaneity. He says, when we say the train going to whatever, well, we don't use trains. That's not, but they use trains. Train going to Santa Barbara leaves at 12 noon. What we mean is that when the train is leaving, okay, the clock will mark 12 noon. This is the simultaneity between two things. So if we cannot agree on simultaneity, we cannot agree in our measurement of time. Time itself changes for different observers. And in fact, we are going to use a light clock to see time dilation of moving clocks. So I will present this. We then are going to see a little bit of a movie in which there is a visualization, much better than the one I can say. And then we are going to derive mathematically by how much time dilates. So assume that there is a light clock. This is a thought clock, right? This is an example that comes from mind. So a ray of light goes between two mirrors. So when the ray of light hits the lower mirror, tick, when it goes up, tack, tick, tack, goes up and down, right? Now, from the observer who is outside, this clock is now moving. So between the tick and the tack, the clock has moved from here to there. Tick, tack, tick. Are you with me? Yes? So now the distance between the tick and the tack is longer. But the speed of light is the same. So how much time elapses between the tick and the tack in this case than in this case? Is it longer or shorter? Longer distance, same speed. So here it will be tick, tack, here will be tick, tack, tick, tack. So the time of moving clocks for an observer who sees the clock passing by, sees it as marking the time with a delay. And this is time itself, it's not only this clock. Let us return to this in a moment.